22 years. That's how long it has been since the Pacific Ocean unleashed a June typhoon powerful enough to make meteorologists stop and stare. Today, that record has been broken. But what makes this storm truly unsettling isn't just its incredible strength, it's the fact that it's still growing. Over the warm waters east of the Philippines, what began as an ordinary tropical disturbance has transformed into a rapidly intensifying monster. In barely more than a day, its winds surged by nearly 60 miles per hour, its pressure collapsed, and satellite images revealed a perfectly organized eye, one of the clearest signs that a tropical cyclone has entered its most dangerous phase. Forecasters are now watching almost hour by hour because every new update raises the same disturbing question. Just how much stronger can this storm become before it finally encounters land? Its projected path is now bending toward Japan, placing millions of people under increasing concern. Yet this story isn't only about one powerful typhoon. Scientists say the real mystery lies beneath it, in the unusually warm Pacific Ocean that supplied the enormous energy needed for such explosive growth weeks before the peak of typhoon season normally arrives. Why is the ocean capable of producing a storm like this so early? Is this simply a rare weather event, or does it reveal something much bigger about the months ahead? In this video, we'll break down exactly how this typhoon became the strongest June storm in 22 years, why it intensified so quickly, where it's expected to go next, what history tells us about storms like this, and why experts across the Pacific are watching the system more closely than almost any other storm in recent memory. Let's begin. The Pacific Ocean has always been capable of producing some of the most powerful storms on Earth. Every year, dozens of tropical systems form across its warm waters, and many never become more than ordinary tropical storms. Others strengthen into dangerous typhoons before eventually fading back into the ocean. It's a cycle meteorologists understand well. They study it every season, watching disturbances develop, tracking changes in wind, pressure, and temperature with remarkable precision. But every once in a while, a storm behaves in a way that even experienced forecasters don't expect. This is one of those storms. Only a few days ago, this system was barely noticeable. It was simply an area of thunderstorms drifting over the Philippine Sea, east of the island of Luzon. Satellite images showed clusters of towering clouds, but nothing suggested that it would soon become the strongest June typhoon seen in more than 22 years. At that stage, meteorologists were monitoring dozens of weather systems across the Pacific, and this one appeared to be following the same slow path that countless tropical disturbances take every year. But then everything changed. Instead of gradually organizing over several days, the storm suddenly found itself in nearly perfect conditions. The surrounding ocean was exceptionally warm. The atmosphere above it remained moist and unstable. Winds high in the atmosphere were unusually favorable. One by one, every obstacle that normally slows a tropical cyclone disappeared. The storm had found an environment almost perfectly designed for rapid growth. Within hours, satellite imagery began revealing dramatic changes. The thunderstorms surrounding the center became increasingly organized. The cloud pattern transformed from a loose collection of storms into a nearly perfect spiral. Meteorologists watched as bands of heavy rain wrapped tightly around the center, feeding enormous amounts of heat into the system. Then something even more remarkable happened. A clear eye began to appear. To most people, the eye of a storm simply looks like a calm circle in the middle of a hurricane or typhoon. But to meteorologists, the appearance of a well-defined eye signals something much more important. It often means the storm has entered an entirely new stage of development. The system is becoming more organized, more efficient, and far more capable of strengthening quickly. Every new satellite image looked more impressive than the last. At the same time, another number was dropping rapidly: the storm's central pressure. Air naturally flows toward areas of lower pressure. The lower that pressure becomes, the faster air rushes inward. Because Earth rotates, that rushing air begins spinning around the center, creating the powerful circulation that defines every tropical cyclone. As the pressure continued falling, wind speeds increased dramatically. Meteorologists watched the numbers climb almost in real time. The storm gained nearly 60 miles per hour in sustained wind speed in little more than a single day. That kind of increase isn't simply considered fast. It's considered explosive. Weather experts have a specific term for this process: rapid intensification. Officially, a tropical cyclone qualifies for rapid intensification when its sustained winds increase by at least 35 miles per hour within 24 hours. It's already considered one of the most dangerous behaviors any tropical cyclone can display because it gives coastal communities far less time to prepare. This storm didn't merely cross that threshold. It exceeded it by an enormous margin. That's when weather agencies across the Pacific began issuing increasingly urgent updates. Forecast models that had predicted a strong typhoon suddenly had to be adjusted upward again and again. Every new satellite pass revealed a storm growing faster than expected. Every advisory forced forecasters to reconsider just how powerful this system might eventually become. And then came the statistic that captured worldwide attention. This had become the strongest June typhoon in 22 years. That number matters because June is not supposed to produce storms like this. Although the Western Pacific is the world's most active tropical cyclone basin, its most violent storms usually occur much later in the season. August, September, and October are typically when the ocean has accumulated enough heat to support the largest and strongest typhoons. June usually serves as the beginning of the season. Storms often develop, but they tend to remain smaller, weaker, and less organized. This year, the Pacific ignored that script. Instead of waiting until late summer, it produced a storm that immediately entered the historical record before the season had truly reached its peak. For experienced meteorologists, that's deeply significant. Weather forecasting isn't just about measuring today's conditions. It's about comparing current events with decades of historical observations. Every storm is measured against thousands that came before it. Patterns repeat. Seasonal cycles emerge. Expectations develop from years of carefully collected data. When a storm breaks a record that has stood for more than 2 decades, forecasters don't simply celebrate a new statistic. They begin asking why. What changed in the atmosphere? Why were conditions so favorable? Was this simply an extremely rare combination of weather, or does it reveal something larger happening across the Pacific Ocean? Those questions became even more urgent because the storm wasn't showing signs of weakening. In fact, official forecasts suggested that additional strengthening remained possible. As long as the typhoon stayed over extremely warm water with favorable atmospheric conditions, there was little preventing it from becoming even more intense. Meanwhile, millions of people across the Western Pacific watched every forecast update with growing concern. Communities in Japan began reviewing emergency plans. Shipping companies adjusted routes across the Pacific. Airlines monitored possible disruptions. Coastal residents followed every advisory, knowing that even small changes in the forecast track could dramatically alter where the strongest winds, highest waves, and heaviest rainfall would eventually strike. Yet despite all the attention focused on the typhoon itself, many scientists believed the storm was only part of the story. The bigger mystery wasn't simply how powerful this cyclone had become. It was why the Pacific Ocean had been capable of producing such an extraordinary storm so early in the season. Because if the ocean was already supplying enough energy to build a record-breaking typhoon in June, one unsettling question naturally followed. What might still be possible once the true peak of typhoon season finally arrives? One question has dominated weather discussions ever since this typhoon began rewriting the record books. How could a storm become this powerful in such a short amount of time? To most people, a typhoon seems like a giant spinning cloud moving across the ocean. But to meteorologists, it's something much more specific. It's an engine, one of the most efficient heat engines found anywhere on Earth. And like every engine, it needs fuel. This storm found more fuel than almost anyone expected. The first ingredient was the ocean itself. If you were standing on a beach looking out across the Pacific, the water beneath this typhoon wouldn't appear unusual. It would simply look calm and blue. But satellites and ocean monitoring buoys revealed something far more important than what the eye could see. The sea surface beneath the storm was extraordinarily warm. In many areas, water temperatures reached between 29 and 30 degrees Celsius, or roughly 84 to 86 degrees Fahrenheit. That may not sound extraordinary at first, but for a tropical cyclone, those few degrees make all the difference. Meteorologists often say tropical cyclones need water temperatures of at least 26.5 degrees Celsius to survive. Think of that number as the minimum requirement, the point where a storm has just enough energy to keep going. But this typhoon wasn't floating over the minimum. It was sitting several degrees above it. That extra warmth acted like pouring premium fuel into a high-performance engine. Every fraction of a degree supplied more energy, more evaporation, and more moisture rising into the atmosphere. And moisture is the true fuel of every tropical cyclone. As sunlight heats the ocean, water continuously evaporates into invisible water vapor. When that vapor rises inside a storm, it cools and condenses into towering thunderstorm clouds. During that process, enormous amounts of hidden energy, known as latent heat, are released. That heat warms the center of the storm. The warmer the center becomes, the lower the air pressure falls. Lower pressure pulls in stronger winds. Stronger winds lift even more warm, moist air. More rising air releases even more heat. The cycle repeats itself over and over again. It's a feedback loop that allows tropical cyclones to grow with astonishing speed once the conditions become favorable. But warm water alone isn't enough. History is filled with storms that moved across very warm oceans yet never became particularly powerful.
Why?
Because another invisible force often tears them apart before they have the chance. That force is called wind shear. Imagine trying to build a tower of blocks while someone keeps pushing the top sideways. No matter how carefully you stack the blocks, the tower begins leaning until it eventually collapses. The same thing happens inside a tropical cyclone. A storm is essentially a giant vertical column of rotating thunderstorms stretching nearly 10 miles into the atmosphere. If strong winds blow in different directions at different heights, they push the upper part of the storm away from the lower part. The entire structure tilts. Its circulation weakens. The organized core begins falling apart. Meteorologists call this vertical wind shear, and it's one of the greatest enemies of tropical cyclones. This storm encountered almost none. The atmosphere surrounding it remained unusually calm. Upper-level winds were weak enough that the storm stayed perfectly upright, allowing its center to remain tightly organized. Nothing disrupted its growth. Nothing pulled it apart. Instead, every thunderstorm forming around the eye remained locked into place, feeding energy directly into the core. But there was still another ingredient working quietly above the storm. Meteorologists often compare tropical cyclones to giant factories. Factories don't simply need fuel coming in. They also need a way for exhaust to leave. If the exhaust becomes trapped inside, the entire operation slows down. Typhoons work the same way. Air rises rapidly through the towering thunderstorms surrounding the eye. Eventually, that air reaches the upper atmosphere, where it must spread outward. Meteorologists call this outflow. If the outflow is blocked, the storm effectively chokes itself. If the outflow is strong, rising air escapes easily, allowing even more warm air to rise from below. This typhoon developed nearly perfect upper-level outflow. Satellite imagery showed air flowing away from the storm in multiple directions, almost like giant invisible rivers carrying exhaust safely away from the center. With warm water below, almost no wind shear, and excellent outflow above, the storm had everything it needed. It was like an aircraft receiving a perfect runway, ideal weather, and unlimited fuel all at once. That's why meteorologists weren't surprised that the storm strengthened. They were surprised by just how quickly it happened. Every few hours, fresh satellite images showed dramatic changes. The eye became clearer. The eye wall, the ring of intense thunderstorms surrounding the eye, grew more symmetrical. Cloud tops became colder, indicating thunderstorms were punching higher into the atmosphere. To trained meteorologists, these weren't just beautiful satellite pictures. They were warning signs. Each improvement in structure suggested the storm was becoming increasingly efficient at converting ocean heat into destructive wind. Another fascinating detail was happening beneath the surface. Many people assume storms only use the warmth at the very top of the ocean. That's only partly true. Powerful typhoons actually churn the sea beneath them. Their enormous winds stir the upper layers of water, mixing warm surface water with cooler water below. If the warm layer is shallow, cooler water quickly reaches the surface. The storm loses its fuel. Its strengthening slows. But this storm wasn't sitting over a shallow, warm layer. Ocean measurements indicated warmth extended surprisingly deep below the surface. Scientists call this ocean heat content. Think of it as the size of the fuel tank rather than just the fuel sitting on top. A shallow tank empties quickly. A deep tank keeps supplying energy long after the engine begins consuming it. This storm had access to a remarkably deep reservoir of heat. Every time its powerful winds stirred the ocean, fresh warm water simply replaced what had been mixed away. The fuel never disappeared. Instead of slowing down, the storm continued accelerating. This is one reason rapid intensification remains one of the greatest challenges in weather forecasting. Predicting where a storm will travel has become increasingly accurate over the past few decades. Modern computer models can often estimate a storm's path several days in advance with impressive precision. But predicting exactly how strong a storm will become is far more difficult. Small differences in ocean temperature, slight variations in wind shear, changes in moisture, or subtle shifts in upper-level winds can dramatically alter how quickly a storm intensifies. Sometimes a forecast expects steady strengthening, only for the storm to explode overnight. Other times, everything appears favorable, yet the storm unexpectedly stalls. Nature still keeps some of its secrets. This time, however, nearly every environmental factor aligned perfectly. The Pacific delivered abundant heat. The atmosphere remained stable. Wind shear stayed unusually weak. Upper-level ventilation remained excellent. The storm itself responded by becoming one of the fastest strengthening typhoons of recent decades. Yet despite everything scientists understood about how the storm grew, one question still remained unanswered. Why was the Pacific Ocean capable of providing this much energy in June? Because if the water beneath this typhoon was already warm enough to support explosive intensification weeks before the traditional peak of typhoon season, then perhaps the most important story wasn't happening inside the storm at all. Perhaps the real story was happening beneath it, in the Pacific Ocean itself. By now, one thing has become clear. This typhoon didn't become one of the strongest June storms in more than 22 years by accident. The atmosphere certainly helped. Weak wind shear, excellent outflow, and a well-organized structure all played important roles. But none of those factors could have produced a storm this powerful without one essential ingredient: the Pacific Ocean. If the storm was the engine, then the ocean was the fuel tank. And according to scientists, that fuel tank was unusually full. When people hear the phrase, warm ocean, they often imagine the water feeling pleasant enough for swimming. But meteorologists see something entirely different. They see stored energy that has been quietly accumulating day after day under the summer sun. Every sunrise adds a little more heat. Every calm day allows the ocean to absorb a little more solar energy. Unlike the atmosphere, which can warm or cool within hours, the ocean changes much more slowly. It stores heat for weeks, months, and sometimes even years. That makes it one of the most important drivers of Earth's weather. The Pacific Ocean is especially important because it contains the largest body of warm tropical water on the planet. Scientists often refer to part of this region as the Western Pacific Warm Pool. It stretches across thousands of miles and contains some of the warmest ocean water found anywhere on Earth. This enormous reservoir acts like a giant battery, storing incredible amounts of heat beneath the surface. Normally, that battery reaches its highest charge later in the year. By August and September, months of tropical sunshine have warmed the upper ocean enough to support the strongest typhoons of the season. That's why late summer has historically produced many of the Pacific's most destructive storms. June is different. June is usually considered the beginning of the season. Storms certainly form, but the ocean hasn't typically stored enough energy to support repeated explosive intensification. That's why this storm surprised so many experts. The Pacific behaved as though it were already several months ahead of schedule. Ocean observations showed sea surface temperatures remaining well above the minimum needed to sustain a tropical cyclone. But temperature at the surface tells only part of the story. The real concern lies beneath. Imagine placing your hand into a swimming pool. If only the top inch of water is warm while everything underneath is cold, stirring the water quickly cools the surface. Now imagine another pool where the warmth extends several feet below. You can stir that water all day, yet it still remains warm. The second pool stores far more energy. The Pacific beneath this typhoon resembled the second example. Scientists measure this hidden energy using something called ocean heat content. Unlike simple sea surface temperature, ocean heat content tells researchers how much warmth exists throughout the upper layers of the ocean. That distinction matters enormously. Powerful typhoons are constantly mixing the water beneath them. Their massive winds churn the ocean, bringing deeper water toward the surface. If colder water rises quickly, the storm loses access to warm fuel. Its strengthening slows. Sometimes it weakens entirely. But when warmth extends deep below the surface, that cooling effect barely happens. Fresh warm water simply replaces what has been mixed away. The storm keeps feeding. That appears to be exactly what happened here. Instead of cooling the ocean beneath itself, the typhoon continued drawing energy from an unusually deep reservoir of warm water. The result was explosive intensification, unlike anything the Pacific had produced in June for more than 2 decades. But this raises an even bigger question. Why was so much heat already stored in the ocean before the peak of typhoon season? Scientists are still studying that answer. Ocean temperatures naturally change from year to year. Large-scale climate patterns such as El Niño and La Niña influence where warm water collects across the Pacific. Ocean currents shift. Trade winds strengthen or weaken. Every season has its own unique combination of atmospheric and oceanic conditions. This year, however, many monitoring stations reported warmer-than-average water across large sections of the western Pacific. Not just one isolated patch. A broad region. That doesn't automatically guarantee stronger storms. Weather is never that simple. Think of the atmosphere as a casino. Every tropical disturbance is like rolling a pair of dice. Warm oceans don't determine the outcome of every roll. They simply increase the chances that one of those rolls produces something extraordinary. Meteorologists are careful about making this distinction. No scientist can honestly point to a single typhoon and claim it was caused by one specific factor. Nature doesn't work that way. Every storm forms because dozens of ingredients come together at exactly the right moment. Ocean temperature, humidity, wind shear, atmospheric pressure, upper-level winds, and countless smaller interactions all combine to determine what eventually happens. Change any one ingredient, and the outcome may be completely different. That's why researchers avoid making sweeping conclusions based on a single event. Instead, they study patterns. One unusually strong storm proves very little. Several years of similar events begin revealing trends. Decades of observations become scientific evidence. That's exactly why this typhoon has attracted so much attention. It isn't simply because it became incredibly powerful. It's because it fits a broader question scientists have been asking for years. Are the oceans providing more opportunities for rapid intensification? Over the last several decades, researchers have observed an increasing number of storms around the world that strengthen dramatically within a short period of time. While scientists continue investigating all the reasons behind this pattern, warmer ocean temperatures and higher ocean heat content are considered important pieces of the puzzle. Rapid intensification remains one of the greatest forecasting challenges because it can transform an ordinary storm into a major disaster within a single day. Communities that expect a Category 1 storm may suddenly face a Category 4. Emergency managers lose valuable preparation time. Evacuations become more difficult. Forecasts require constant updates. That's why every new example matters. This typhoon is now part of that growing body of evidence scientists are studying, not as proof of one specific theory, but as another valuable observation in a much larger picture. Meanwhile, satellites continue measuring the Pacific every hour. Weather buoys transmit fresh temperature readings. Research vessels monitor changes in ocean currents. Supercomputers process millions of data points every day. And despite all this technology, one simple truth remains. The Pacific still has the power to surprise us. The strongest June typhoon in 22 years formed because every critical ingredient aligned almost perfectly. But perhaps the most unsettling realization is this. The ocean that fueled this storm isn't disappearing tomorrow. Typhoon season is only beginning. The Pacific remains warm. The deep reservoir of heat remains in place. And if another tropical disturbance enters the same favorable environment in the weeks ahead, it may find the very same fuel that transformed an ordinary cluster of thunderstorms into one of the most remarkable June typhoons of the modern era. That realization shifts attention away from the storm itself and toward the people now waiting in its projected path. Because while scientists continue studying why the Pacific built this monster, millions of residents across southern Japan have a far more immediate concern. Where is it going next? By now, the biggest question is no longer how this typhoon became so powerful. The question millions of people are asking is far more immediate. Where is it going? Unlike an earthquake, which strikes without warning, a typhoon gives us something incredibly valuable: time. Modern satellites can monitor every movement almost continuously, while advanced computer models calculate thousands of possible future paths every few hours. Yet even with all this technology, forecasting a storm's exact track is never as simple as drawing a single line across a map. That's because a typhoon doesn't decide where it wants to go. It is carried. High above the storm, invisible rivers of air stretch across the atmosphere. These enormous steering currents push tropical cyclones across the ocean, much like ocean currents carry ships across the sea. The storm itself is powerful, but compared to these vast atmospheric patterns, it is surprisingly small. One of the most important steering systems is something meteorologists call the subtropical ridge. Although most people have never heard the name, this enormous area of high pressure influences the paths of countless Pacific typhoons every year. You can't see it from the ground, but weather satellites and atmospheric observations reveal its presence clearly. Think of the subtropical ridge as a giant invisible wall. A typhoon cannot simply move through it. Instead, the storm travels around its edges. When the ridge is positioned farther north, storms often continue westward toward countries like the Philippines, Taiwan, or China. When the ridge weakens or shifts eastward, storms begin curving toward the north. Meteorologists call this movement recurvature. It's one of the defining characteristics of many western Pacific typhoons. That is exactly what this storm is now doing. During its early development, the typhoon moved generally west-northwest over the Philippine Sea. At first, there were concerns that it might continue directly toward Luzon in the northern Philippines. Fortunately, the steering pattern began changing. Rather than continuing west, the subtropical ridge allowed the storm to turn northward. That single change dramatically altered the forecast. Instead of aiming directly at the Philippines, the typhoon began bending towards southern Japan. For residents of Luzon, this represented an enormous relief. A direct landfall from a storm of this intensity could have produced catastrophic wind damage, widespread coastal flooding, and life-threatening storm surge. Instead, the latest forecasts suggest the storm center should remain offshore. That doesn't mean the Philippines are completely safe. Far from it. Even without a direct landfall, a typhoon this large influences weather hundreds of miles away. Its enormous circulation pulls moisture into the southwest monsoon, increasing rainfall across portions of the northern Philippines. Heavy downpours can quickly trigger flash floods, swollen rivers, and landslides, especially in mountainous regions where saturated soil becomes unstable. Along the coastline, dangerous waves and powerful rip currents can develop long before the center of the storm arrives anywhere nearby. Sometimes the ocean becomes deadly even while skies remain relatively calm. Meanwhile, attention has shifted farther north. The current forecast places Okinawa and the Sakishima Islands among the areas facing the greatest potential impacts. These islands sit directly within one of the world's busiest typhoon corridors. Residents there are no strangers to powerful tropical cyclones. Homes are built with stronger construction standards. Emergency shelters are well established. Warning systems are highly organized. Many families keep emergency supplies ready every typhoon season because severe storms are considered a normal part of life. Preparation, however, does not eliminate danger. A powerful typhoon remains capable of producing enormous destruction even in communities accustomed to these events. The first threat is wind. Sustained hurricane-force winds can tear roofing from buildings, shatter windows, topple trees, and bring down electrical infrastructure across large areas. Even objects that seem harmless, a bicycle, a rooftop panel, a loose sign, or a small branch, can become dangerous airborne projectiles. The second threat comes from water. In fact, water often proves deadlier than the wind itself. As the storm approaches land, its powerful circulation pushes seawater toward the coastline. This is known as storm surge. Unlike ordinary waves, storm surge is a massive rise in sea level capable of flooding entire neighborhoods within minutes. Combined with high tide, it can overwhelm coastal defenses and force seawater far inland. Then comes the rainfall. Typhoons are essentially giant water pumps. They lift enormous quantities of moisture from the ocean and release it over land. Hours of relentless rainfall can overwhelm drainage systems, trigger flash flooding, and destabilize steep hillsides. Mountain communities face an additional danger. When heavy rain saturates soil that already rests on steep slopes, landslides become increasingly likely. Entire sections of hillside can suddenly collapse, destroying roads, homes, and critical infrastructure. Even after the strongest winds pass, flooding and landslides often continue for many hours. Then there is the ocean itself. Far from the center of the storm, waves continue growing. Massive swells spread outward in every direction. Fishing vessels return to port. Commercial shipping adjusts routes. Ferries suspend operations. Even experienced sailors know that confronting a mature typhoon at sea is one of the most dangerous situations imaginable. Despite all these preparations, one important uncertainty remains. Exactly how close will the center pass? Many people assume forecast tracks are fixed. They're not. When you see a forecast cone on television, it doesn't represent the size of the storm. It represents uncertainty. The center could travel anywhere within that cone depending on subtle changes in the atmosphere. A shift of only 50 or 100 miles may not seem significant on a map of the Pacific. For communities near the coast, it can make an enormous difference. If the strongest part of the eye wall remains offshore, damage may be relatively limited. If the eye passes directly overhead, conditions become dramatically more severe. Small changes in track often determine where the highest winds, largest storm surge, and heaviest rainfall occur. That's why meteorologists continuously update their forecasts every few hours. They aren't changing their minds. They're incorporating new satellite observations, aircraft data, ocean measurements, and computer model calculations as the storm evolves. Forecasting is a process of refinement. Each new observation improves the picture. Another important factor is intensity. Current projections indicate the typhoon should gradually weaken as it moves farther north. The reason is straightforward. The farther north the storm travels, the cooler the ocean becomes. At the same time, upper-level winds generally increase, introducing more wind shear that disrupts the storm structure. Together, these factors usually weaken tropical cyclones before they approach mainland Japan. That is certainly encouraging news. But forecasters remain cautious. Nature does not always follow expectations perfectly. Sometimes storms weaken faster than predicted. Other times they hold their strength much longer than expected. A slightly warmer patch of ocean, a temporary reduction in wind shear, or internal changes within the storm itself can all influence how much intensity is lost before landfall. That's why emergency officials consistently encourage residents to prepare for the stronger end of the forecast rather than hoping for the weakest outcome. It's always better to prepare for conditions that never arrive than to be caught unprepared by conditions that do. For now, millions of people across southern Japan continue watching every advisory, every satellite image, and every forecast update. Because although the storm's exact path may still change slightly, one thing is already certain. This isn't simply another routine typhoon. It is one of the strongest June storms the Pacific has produced in more than 2 decades. And as it continues moving northward, history itself offers a remarkable comparison. The last time a June typhoon reached this level of intensity, it became one of the defining storms of an entire season. To understand why meteorologists keep mentioning that 22-year record, we have to go back in time and revisit the last storm that earned the same distinction. Hospitals can activate emergency procedures earlier. These improvements don't make typhoons less dangerous, but they do make societies more resilient. Still, forecasting intensity remains one of weather science's greatest challenges. Even today, meteorologists sometimes underestimate how quickly a storm can strengthen. Rapid intensification continues to surprise even the world's most advanced forecasting systems. That's exactly what happened with this typhoon. Although forecasters recognized favorable conditions, the storm's explosive strengthening exceeded many early expectations. Its transformation reminded scientists that despite decades of technological progress, the atmosphere still holds surprises. History teaches another valuable lesson as well. One extraordinary June storm does not automatically determine what the rest of the season will bring. The historic season 22 years ago included additional significant typhoons, but every year develops differently. Some seasons begin quietly before becoming extremely active. Others start aggressively and later weaken. Sometimes one remarkable storm becomes the defining event of an otherwise average year. Other times it serves as only the beginning of a long series of powerful cyclones. That's why seasonal forecasting is so complex. Meteorologists cannot look at one storm and confidently predict everything that follows. Instead, they continue monitoring larger patterns across the Pacific. Ocean temperatures, atmospheric circulation, wind shear, humidity, pressure systems. Together, these ingredients determine whether future disturbances encounter the same favorable environment. For now, today's typhoon has already earned its place in the historical record. Whether it ultimately becomes one of the defining storms of the year remains uncertain. But one thing is beyond debate. It has reminded scientists, emergency managers, and millions of people living around the Pacific that nature still possesses the ability to produce extraordinary events when all the right conditions align. And perhaps the most important lesson history offers is not about fear. It's about preparation. Every record-breaking storm leaves behind new data. Every season teaches scientists something new. Every forecast becomes slightly more accurate because of the storms that came before. As this typhoon continues its journey, researchers around the world are collecting every possible observation, hoping to better understand not only this remarkable cyclone but also the next one that will inevitably form over the vast waters of the Pacific. Because while history helps explain what has already happened, the future of this typhoon season depends on a different question altogether. What do scientists actually know? And just as importantly, what don't they know about storms this powerful? When meteorologists say this is the strongest June typhoon in 22 years, they aren't using that comparison simply because it sounds dramatic. They're using it because records matter. Every storm that forms over the Pacific becomes part of an enormous historical archive. Scientists compare each new cyclone with thousands that came before it, measuring wind speeds, central pressure, rainfall, storm surge, and countless other details. These comparisons help reveal whether a storm is truly extraordinary or simply another powerful system in an active basin. This typhoon stood out immediately. To understand why, we have to go back more than 2 decades. The early 2000s produced several memorable typhoon seasons, but one June storm quickly separated itself from the rest. At a time when forecasters expected only the gradual beginning of the season, a tropical disturbance found nearly perfect conditions over the western Pacific. Much like today's storm, it strengthened at an astonishing pace, surprising meteorologists who believed there simply wasn't enough energy available that early in the year to support such explosive development. Yet nature proved otherwise. Within days, that storm evolved from an ordinary tropical system into one of the most powerful June typhoons on record. Weather satellites from that era lacked some of the advanced technology available today. Forecast models were improving, but they couldn't match the accuracy of modern supercomputers. Meteorologists relied heavily on satellite imagery, ship reports, weather buoys, and specialized intensity estimates to monitor rapidly changing conditions. Even with those limitations, one fact became impossible to ignore. The storm had reached a level rarely seen during June. As it crossed the Pacific, forecasters watched its eye become remarkably well organized. Dense rings of thunderstorms wrapped tightly around the center, while the surrounding atmosphere allowed the cyclone to maintain its strength far longer than many expected. Communities along its projected path suddenly found themselves facing a storm that had intensified much faster than early forecasts suggested. Emergency officials had to adjust preparations quickly. Warnings were upgraded. Evacuation plans expanded. Shipping companies altered routes. Airlines canceled flights. Ports suspended operations as enormous waves spread across the western Pacific. The storm ultimately produced destructive winds, widespread flooding, dangerous storm surge, and significant disruptions across parts of East Asia. In several locations, rainfall continued long after the strongest winds had passed, causing rivers to overflow and triggering landslides in mountainous terrain. For many residents, the flooding became just as devastating as the wind itself. Entire neighborhoods were temporarily isolated. Roads disappeared beneath muddy water. Power outages affected hundreds of thousands of people. Recovery continued for weeks after the skies finally cleared. Although engineering standards and emergency planning have improved dramatically over the last 2 decades, the storm remains firmly embedded in meteorological history because of one simple fact. It showed just how dangerous an early-season typhoon could become. That lesson remains just as important today. When scientists compare today's typhoon with that historic June storm, they aren't suggesting history is repeating itself exactly. No two tropical cyclones are ever identical. Every storm follows its own path. Every atmosphere is unique. Ocean temperatures change. Steering currents evolve. Population centers grow. Infrastructure improves. Even small differences can completely alter the final outcome. That's why responsible meteorologists avoid making direct one-to-one predictions. Instead, they compare the environmental conditions. They ask questions like, how warm was the ocean? How quickly did the pressure fall? How rapidly did the winds increase? How symmetrical did the eye become? How favorable was the upper atmosphere? These comparisons provide context rather than certainty. In several of these categories, today's storm resembles that historic June typhoon remarkably closely. Both storms experienced explosive rapid intensification. Both developed over exceptionally warm western Pacific waters. Both displayed highly organized satellite structures. Both reached extraordinary intensity unusually early in the season. Those similarities explain why experienced forecasters immediately began discussing the 22-year record. But there are also important differences. Today's meteorologists possess tools that simply didn't exist 2 decades ago. Modern weather satellites capture incredibly detailed images every few minutes. Ocean monitoring satellites measure sea surface temperatures across enormous regions. Thousands of drifting buoys continuously report water temperatures and wave heights. Reconnaissance aircraft, where available, gather detailed atmospheric measurements. Powerful computer models process millions of calculations every hour. Artificial intelligence now assists researchers in identifying subtle changes that human forecasters might overlook. All of these technologies provide emergency managers with earlier warnings than were possible 20 years ago. That improvement saves lives. Forecast tracks today are dramatically more accurate than they were at the beginning of the century. Communities often receive several extra days to prepare. Evacuation decisions can be made with greater confidence. Emergency supplies can be positioned in advance. Search and rescue teams can mobilize before disaster strikes. Whenever a powerful typhoon captures global attention, something predictable happens. The storm doesn't stay confined to weather forecasts. It spreads across social media. Within minutes of dramatic satellite images appearing online, thousands of posts begin circulating. Some share official warnings from meteorological agencies. Others post videos of towering waves or darkening skies. But mixed among the accurate information are claims that range from misleading to completely false. Some people insist storms like this cannot occur naturally. Others claim governments are secretly controlling the weather. Some believe satellites are hiding the storm's true strength, while others argue that weather agencies intentionally exaggerate forecasts to create panic. These claims spread quickly because powerful storms inspire powerful emotions. When people witness nature producing something extraordinary, many naturally search for extraordinary explanations. But weather science tells a very different story. Let's begin with one of the most common questions. Can a typhoon actually be created by humans? The short answer is no. Scientists have studied tropical cyclones for decades, and while humans can influence certain aspects of the environment over long periods of time, there is no technology capable of creating, steering, or rapidly intensifying a storm the size of a major typhoon. To understand why, consider the amount of energy involved. A mature typhoon releases heat energy on a scale almost impossible to imagine. Every single day, it transfers energy equivalent to many thousands of large power plants operating simultaneously. The amount of water evaporated, condensed, and circulated through the storm is measured in billions of tons. No existing machine, aircraft, satellite, or experimental technology comes remotely close to generating that amount of energy. Nature is doing the work. The storm builds itself by extracting heat from the ocean. The atmosphere simply provides the right conditions. That doesn't mean scientists don't influence weather at all. Cloud seeding, for example, has been used in limited situations to encourage rainfall from existing clouds. It may slightly increase precipitation under specific conditions, but it cannot build a typhoon from nothing. Nor can it transform an ordinary tropical disturbance into a record-breaking cyclone. The scale is completely different. It's the difference between lighting a candle and powering an entire city. Another myth appears almost every time a major storm develops. Some people believe weather agencies intentionally hide the real wind speeds. Others notice that different organizations report different numbers and assume someone must be wrong. The reality is much simpler. Different meteorological agencies use different methods for averaging sustained wind speeds. For example, some agencies calculate average winds over 1 minute. Others use 10-minute averages. Both methods are scientifically valid. Neither is dishonest. Imagine timing two runners. One person records their fastest speed over 10 seconds. Another measures their average speed over an entire minute. Both measurements describe the same runner, but the numbers won't match exactly. Typhoon wind measurements work in much the same way. That's why reports from different countries may appear different even when they're describing the very same storm. Another common misunderstanding involves forecast changes. When people see a storm's projected path shift from one day to the next, they sometimes conclude that meteorologists don't know what they're doing. In reality, changing forecasts often demonstrate that the forecasting system is working exactly as intended. Weather prediction is never a single calculation. Every few hours, satellites provide fresh observations. Ocean buoys report new temperatures. Weather balloons collect atmospheric measurements. Aircraft gather additional information when available. Computer models process millions of new calculations using that updated data. Each forecast becomes a little more accurate than the one before it. Think of driving through heavy fog. At first, you can only see a short distance ahead. As you continue moving forward, more of the road becomes visible. You aren't changing the road. You're simply seeing it more clearly. Forecasting works the same way. Meteorologists continuously refine their predictions as better information becomes available. Another question often asked is surprisingly simple. If satellites can see the storm, why don't they measure everything perfectly? The answer lies in what satellites actually observe. A weather satellite doesn't directly measure wind speed by looking at spinning clouds. Instead, scientists combine multiple techniques. Visible satellite images reveal cloud structure during daylight. Infrared sensors measure cloud top temperatures. Microwave instruments peer through thick cloud layers. Scatterometers estimate winds over the ocean surface. When available, reconnaissance aircraft fly directly into storms, releasing instruments that measure pressure, temperature, humidity, and wind throughout the atmosphere. Meteorologists then combine all these observations with sophisticated computer models to estimate a storm's intensity. It's an incredibly advanced process. But it's still an estimate. Nature rarely offers perfectly simple answers. One reason rapid intensification remains so difficult to forecast is because many of the critical changes happen inside the storm itself. Eye-wall replacement cycles. Small pockets of dry air. Tiny shifts in wind direction. Changes in thunderstorm organization. These internal processes can dramatically influence whether a storm strengthens, weakens, or maintains its intensity. Sometimes a cyclone appears perfectly healthy from space, yet unexpectedly weakens overnight. Other times, it suddenly explodes in strength despite only subtle changes visible on satellite imagery. Scientists continue researching these mysteries every year. Modern forecasting has improved enormously compared with just 20 years ago, but predicting intensity remains one of the greatest unsolved challenges in tropical meteorology. Perhaps the most dangerous myth of all is the belief that forecasts are always either completely right or completely wrong. Weather simply doesn't work that way. Every forecast includes uncertainty. Meteorologists openly communicate that uncertainty through forecast cones, probability maps, rainfall estimates, and confidence levels. Those aren't signs of weakness. They're signs of scientific honesty. Researchers recognize the atmosphere as an extraordinarily complex system. Rather than pretending to know everything, they explain what they know, what they don't know, and how likely different outcomes may be. That transparency allows emergency managers to make informed decisions. Preparing for uncertainty is often far safer than assuming certainty where none exists. This is especially true with a storm like this one. Scientists agree on several important facts. The Pacific Ocean supplied exceptional amounts of heat. Atmospheric conditions strongly favored rapid intensification. The typhoon strengthened at an extraordinary rate. Its early season intensity is historically unusual. Those conclusions are supported by satellite observations, ocean measurements, atmospheric data, and decades of scientific research. At the same time, scientists continue studying why some storms intensify faster than expected, why certain systems weaken unexpectedly, and how changing ocean conditions influence future tropical cyclones. Science is not a collection of final answers. It is a process of continually improving our understanding of the natural world. Every powerful typhoon becomes another opportunity to learn. Every new satellite pass adds another piece to the puzzle. Every season improves future forecasts. And while this remarkable storm has already challenged expectations, it has also provided scientists with valuable data that may help protect lives during the storms yet to come. Because as extraordinary as this typhoon has been, the most important question now shifts from what has already happened to what may happen next. Is this simply one remarkable storm in an otherwise ordinary year? Or is it the first sign that the Pacific's 2026 typhoon season is only beginning to reveal its true potential? With a typhoon this powerful forming so early in the year, one question naturally follows. What does this mean for the rest of the season? It's a question meteorologists hear every time an extraordinary storm appears on weather maps. After all, if June has already produced one of the strongest typhoons in more than 2 decades, does that mean the Pacific is heading toward an unusually dangerous year? The honest answer is both simple and complicated. No single storm can predict an entire season. Weather doesn't work that way. Imagine flipping a coin 10 times. Getting heads on the first flip doesn't guarantee what the next 9 flips will be. Each one depends on its own conditions. Tropical cyclones behave in a similar way. Every storm forms only when the atmosphere and the ocean come together in just the right combination. A record-breaking June typhoon is certainly unusual. But it is not, by itself, proof that every storm that follows will also become historic. Still, scientists are paying close attention because this storm has revealed something important. It has shown that the Pacific Ocean is already capable of supporting explosive intensification. That matters. Every typhoon season begins with certain background conditions already in place. Meteorologists monitor those conditions months before the busiest part of the season arrives. They study sea surface temperatures, deep ocean heat content, wind patterns, atmospheric moisture, and large-scale climate systems stretching across thousands of miles. These ingredients don't determine exactly how many storms will form, but they influence the environment in which future storms will develop. Think of the Pacific as a giant kitchen. The ingredients may already be sitting on the counter. Warm water, moist air, favorable atmospheric circulation. Whether those ingredients actually become another powerful typhoon depends on when, and if, a tropical disturbance enters the picture. Without a disturbance, nothing happens. With the right disturbance at exactly the right time, another powerful storm can emerge surprisingly quickly. That's why meteorologists never stop monitoring the Western Pacific. Unlike some ocean basins that experience long quiet periods, the Western Pacific remains the most active tropical cyclone region on Earth. Every year, dozens of tropical depressions form across its warm waters. Many weaken before threatening land. Others grow into destructive typhoons. A few become legendary. Historically, the busiest months are August and September. During those months, the ocean has absorbed maximum summer heat. Atmospheric conditions often become even more favorable for tropical development, and the frequency of storms typically increases. This year, however, June has already demonstrated that the Pacific possesses an unusually large reservoir of available energy. That doesn't guarantee an active late season, but it certainly gives scientists another reason to monitor conditions closely. One factor researchers continue watching is ocean heat content. As long as deep warm water remains across large sections of the Western Pacific, future storms may continue finding abundant fuel beneath them. Remember, tropical cyclones don't simply use the temperature at the ocean surface. They draw energy from the upper layers of the sea. If that warmth extends deep below the surface, storms have a greater opportunity to maintain or even increase their intensity. Meteorologists are also watching wind shear. Throughout the season, wind patterns naturally change. Some weeks produce calm atmospheric conditions that favor tropical development. Other weeks introduce strong upper-level winds that disrupt developing systems before they become organized. Even if the ocean remains exceptionally warm, strong wind shear can dramatically reduce the number of major typhoons. That's why no responsible scientist predicts an entire season based on ocean temperatures alone. Another important influence comes from large-scale climate patterns such as El Niño and La Niña. These natural cycles alter atmospheric circulation across the Pacific, shifting where storms are more likely to form and how they may travel. Some years favor more westward-moving typhoons. Other years encourage storms to curve northward earlier. Researchers continuously monitor these changing patterns because even subtle shifts can influence an entire season. Then there's humidity. Dry air is one of a tropical cyclone's greatest enemies. When dry air enters the circulation, it can weaken thunderstorms inside the storm, slowing development or even causing a system to collapse. Moist tropical air, on the other hand, provides the continuous supply of water vapor needed to fuel towering thunderstorm clouds. Throughout the coming months, scientists will watch moisture levels across the Pacific just as carefully as they monitor ocean temperatures. One reason this season has attracted so much attention is because rapid intensification has become an increasingly important forecasting challenge. Communities can often prepare for a slowly strengthening storm several days in advance. Rapid intensification changes everything. A storm expected to remain moderate may suddenly become extremely dangerous within 24 hours. Emergency managers have less time. Evacuation decisions become more urgent. Residents must react much faster. This June typhoon has already demonstrated exactly how quickly that transformation can occur. That lesson will remain in the minds of forecasters throughout the rest of the year. Every new tropical disturbance will receive especially careful attention. If another developing storm encounters the same favorable combination of warm water, low wind shear, and moist air, meteorologists know rapid strengthening is once again possible. That doesn't mean panic. It means vigilance. Modern forecasting systems are better than ever before. Weather satellites monitor the Pacific around the clock. Ocean buoys continuously transmit temperature and wave data. Computer models analyze millions of calculations every few hours. Artificial intelligence increasingly assists meteorologists in identifying subtle trends hidden within enormous datasets. Together, these tools give forecasters an unprecedented view of developing storms. Yet despite all this technology, nature continues reminding us of one important truth. The atmosphere still contains surprises. No computer model can eliminate uncertainty completely. No forecast can predict every internal change occurring inside a rapidly intensifying cyclone. Every season presents new puzzles. Every remarkable storm teaches scientists something new. For communities living across Japan, Taiwan, the Philippines, China, and countless Pacific islands, this reality reinforces an important principle. Preparation should never begin when a storm is already approaching. The best time to prepare is long before a warning is issued. Emergency supplies, family communication plans, knowledge of evacuation routes, understanding local flood risks. These simple preparations save lives regardless of whether the season ultimately becomes quiet or active. As this remarkable typhoon continues moving northward, researchers across the world will keep studying every piece of information it provides. Its satellite imagery, its wind field, its rainfall, its interaction with the ocean, its weakening process. Each observation will become part of a growing scientific record designed to improve future forecasts. Because storms like this are remembered for more than their strength. They become milestones in our understanding of how the atmosphere and oceans work together. And while the rest of this season remains unwritten, one lesson has already become unmistakably clear. The Pacific has reminded the world that even after decades of scientific progress, it still possesses the power to produce events that exceed expectations. The question now is no longer whether this typhoon has made history. It already has. The final question is what lasting lesson humanity will take from one of the strongest June storms in more than 22 years, and how that lesson may shape the way we prepare for the storms of the future. As this remarkable typhoon begins to lose strength over cooler waters, it's easy to think the story is coming to an end. But in many ways, the most important part of the story is only beginning. long after the final warning is cancelled, long after the floodwaters recede, and long after damaged buildings are repaired. Scientists will still be studying this storm. Every satellite image, every ocean measurement, every wind observation, and every forecast update will become part of a growing archive that helps researchers better understand how some of the world's most powerful storms develop. That's because every extraordinary typhoon teaches us something new. No two storms are ever exactly alike. Some become famous because of the destruction they leave behind. Others are remembered because they changed the way meteorologists understand the atmosphere. A few managed to do both. This June typhoon has already earned its place among those unforgettable storms. Not simply because it became one of the strongest June typhoons in more than 22 years, but because it reminded scientists that nature still has the ability to surprise us. For decades, forecasting has improved at an incredible pace. Today's meteorologists have access to technologies that previous generations could only imagine. Weather satellites circle the Earth around the clock, capturing detailed images every few minutes. Ocean monitoring buoys continuously transmit water temperatures, wave heights, and atmospheric pressure. Powerful Doppler radar systems track rainfall and wind as storms approach land. Research aircraft fly directly into tropical cyclones, collecting measurements from inside the eye itself. Supercomputers process enormous amounts of weather data every hour, running multiple forecast models that simulate thousands of possible future scenarios. Artificial intelligence is beginning to help identify hidden patterns that might otherwise go unnoticed. Together, these tools have transformed weather forecasting. 40 years ago, predicting the exact path of a typhoon several days in advance was far more difficult than it is today. Forecast errors were much larger. Communities often had less warning. Emergency managers faced greater uncertainty. Today, track forecasts have become remarkably accurate. In many cases, meteorologists can predict where a storm will travel several days before landfall with impressive precision. That improvement has saved countless lives. But forecasting where a storm will go is only part of the challenge. Predicting how powerful it will become remains one of the greatest mysteries in modern meteorology. Rapid intensification continues to surprise scientists around the world. A tropical storm that appears relatively harmless in the morning can become a dangerous major typhoon by the following day. Sometimes every forecast model expects steady strengthening, only for the storm to explode far beyond expectations. Other times, the opposite happens. A storm expected to become extremely powerful suddenly weakens for reasons that aren't immediately obvious. Nature rarely follows a perfectly predictable script. This uncertainty isn't a weakness of science. It's a reminder of the incredible complexity of Earth's atmosphere. Every tropical cyclone depends on thousands of interacting factors. Ocean temperatures, deep ocean heat content, atmospheric moisture, wind shear, upper-level outflow, internal thunderstorm organization, eye wall replacement cycles, dry air intrusions, ocean currents. Even tiny changes in one of these ingredients can alter the storm's future. Scientists continue working to understand these interactions more completely. Every major typhoon provides valuable new information. This storm is no exception. Researchers will spend months analyzing why it intensified so rapidly. They will compare satellite observations with computer simulations. They will examine ocean temperatures beneath the storm. They will study atmospheric conditions hour by hour. The goal isn't simply to understand this typhoon. The goal is to improve forecasts for the next one. Because there will always be another one. The Pacific Ocean has produced powerful typhoons for thousands of years. It will continue producing them long after this season has ended. Humanity cannot stop them from forming. We cannot control where they travel. And we certainly cannot eliminate the enormous energy stored within the tropical oceans. But we can continue improving how we respond. That may be the greatest lesson of all. Throughout history, the deadliest storms often became disasters because people received little warning. Entire communities were caught completely by surprise. Communication systems were limited. Forecasts were uncertain. Evacuations began too late. Today, millions of people receive emergency alerts directly on their phones. Weather agencies share real-time satellite imagery online. Television stations interrupt programming to broadcast warnings. Social media allows emergency information to spread within seconds. Local governments coordinate evacuations with far greater efficiency than ever before. Preparedness has become just as important as prediction. And that preparedness saves lives. Of course, no warning system is perfect. No forecast can remove every risk. Storm surge can still overwhelm coastlines. Floodwaters can still rise faster than expected. Landslides can still occur without warning. Powerful winds can still damage even well-built structures. Nature always deserves respect. But fear alone has never protected anyone. Preparation does. Knowing evacuation routes. Keeping emergency supplies ready. Listening to official weather updates. Understanding local flood risks. These simple actions often make the greatest difference when a powerful storm approaches. Perhaps that's the most valuable lesson this remarkable typhoon leaves behind. Its incredible strength captured headlines around the world. Its rapid intensification challenged forecasting systems. Its satellite images amazed meteorologists. Its early-season timing surprised even experienced scientists. But beyond all the records and statistics lies a much simpler truth. The atmosphere and the ocean remain connected in ways we are still learning to fully understand. Every storm reminds us that Earth is a dynamic planet, constantly changing, constantly moving, and constantly teaching us new lessons. The strongest June typhoon in more than 22 years will eventually weaken. Its clouds will disappear. Its eye will collapse. Its winds will fade into ordinary weather. But the knowledge gained from this storm will remain. Scientists will use it to improve computer models. Emergency planners will review their response strategies. Engineers will evaluate infrastructure. Communities will remember the importance of preparation. And meteorologists will carry these lessons into every forecast they make during the rest of this season and beyond. Because in the end, history doesn't remember every storm equally. Some storms are remembered because they broke records, others because they changed lives, and a rare few are remembered because they changed the way we understand nature itself. This extraordinary June typhoon may ultimately be remembered for all three reasons. When this typhoon first appeared over the western Pacific, it looked like countless other tropical disturbances that form every year. Few people imagined it would become one of the strongest June typhoons seen in more than 22 years. Yet within just a matter of days, it transformed into a storm powerful enough to capture the attention of meteorologists, emergency officials, and millions of people across the region. Throughout this video, we've seen how a combination of exceptionally warm ocean waters, deep ocean heat content, weak wind shear, and nearly perfect atmospheric conditions allowed this storm to strengthen with astonishing speed. We've explored why rapid intensification remains one of the greatest challenges in weather forecasting, why southern Japan has been preparing for possible impacts, and why scientists are carefully studying every piece of data this storm leaves behind. But perhaps the biggest lesson isn't about one typhoon alone. It's about understanding the incredible power of the Pacific Ocean and respecting the forces of nature that continue shaping our world. Every record-breaking storm reminds us that while forecasting technology has advanced tremendously, nature still has the ability to surprise even the most experienced experts. The good news is that today's warning systems, satellite technology, and emergency planning are more advanced than ever before. Every improvement in forecasting gives communities more time to prepare, helping protect lives when the next powerful storm inevitably forms. Some storms become historic because of the places they strike. Others become historic because of what they teach us. This typhoon may ultimately be remembered for both. If you found this breakdown helpful, be sure to subscribe for more in-depth weather and science documentaries. Let us know in the comments where you're watching from and whether your region experiences typhoons, hurricanes, or other extreme weather events. Stay informed, stay prepared, and we'll see you in the next video.